doesn't realize it.
So the last thing we want to talk about is the normality rule. So we started by, from experiments, this was noticed, or this was assumed and verified by the experiments, the plastic strain components are related to the deviatoric stress applied on the material. And from this, we realized that this is equivalent to saying that the plastic strain components are obtained from a plastic potential function, and this plastic potential function is the yield function. And this is called the associated flow rule. And this associated flow rule directly leads to what we call the normality rule. It's a direct consequence of the associated flow rule. So the normality rule So what we're saying is that epsilon dot plastic Ij is equal to a number, and this number, let's write this number, this plastic strain parameter multiplied by partial phi by partial sigma j. Now partial phi by partial sigma j, I'm going to draw the yield function in the stress space. I'm going to use the principal stresses because I have 3 principal stresses, so I can visualize it in the principal stresses space, but you can look at it as in a space of 9 dimensions, sigma, in the dimension having sigma 1, sigma 2, sigma 3, 3, and sigma 2, and so on. Now on the yield surface, phi is equal to 0. Because phi is the yield surface. Phi is equal to sigma non-mesos minus sigma yield. On the yield surface, all these points are 0. So this is the direction of constant phi. And if you remember the gradient of field, if phi is a field, the gradient of phi is perpendicular to the direction of the constant phi. If you don't remember this, we know that, let's say, this is point sigma, this is sigma plus h n, where n is a vector, h is a number, phi of sigma plus plus hn is equal to 0. The yield function at this point is equal to 0, and the yield function at this point is also equal to 0. This is equal to the gradient of phi, nothing. And so the gradient of phi, with respect to its parameters, sigma and the stresses, is perpendicular to the direction of constant phi. And this is the normality rule. Gradient of phi is perpendicular everything I said today. So the gradient of phi is perpendicular to the yield surface. We know that phi is a function of the stress and gives me a number. You can look at phi as if it's a function from r power 9 to r. The gradient of phi is equal to the gradient of phi with respect to sigma g. This is perpendicular to the surface phi equal constant. Because it's perpendicular to the surface phi equal constant on the yield surface, phi equals 0 equal constant, and so the gradient of phi is perpendicular to the surface. So this is the gradient of phi. And we just said that the strain parameters epsilon Pij is equal to partial phi by partial sigma g multiplied by this parameter. if we draw the components of this in the stress space, these components will be normal to the yield surface. And so if you draw plastic stream, P, the vector made out of the different components is perpendicular, the direction is perpendicular to this yield surface. This is called normality rule, and is a direct consequence the associated flow rule, which was a direct consequence of the assumption delta epsilon Pij is equal to delta lambda multiplied by Sij. First, we assume epsilon plastic, the components are directly proportional to Sij, and we realize that this means that the epsilon plastic Ij is obtained from a plastic potential function associated with the yield function. And from this, we also realize that that means that the plastic strain components are perpendicular to the yield function. Yes?
Is there some sort of physical meaning to normality rule? That's
The physical meaning here is that these components do not have any that this vector does not have any, that its projection on this line is 0, which is important. The projection of this on this line is 0 means that the sum is equal to 0. The sum of the epsilon. So it means delta epsilon P11 plus delta epsilon P22 plus delta epsilon P33 equal to 0. This is what's nice about it. This is why it's physically important, because it differentiates the plasticity of soils and plasticity of concrete, whereas you plastify, the volume increases or decreases, from the plasticity of metal, where the volume does not change. And the normality rule ensures this, because the yield surface in metals is concentric around the line of sigma 1 equal to sigma 2 is equal to sigma 3. So you get a cylinder around this line, and the normality rule ensures that the plastic strain component, the components of the plastic strain are perpendicular to this line. They're perpendicular to this line, so you don't have any, that means they don't have any component. That basically means that the sum of these is 0. But you're looking, I mean, I'm telling you the significance of this, I'm not telling you what it means physically.
Oh yeah, I'm just trying.
Yeah, I'm just saying I'm not even answering your question.
Well, it's sort of, yeah, it certainly does answer it, because I'm trying to grasp.
Yes. But yeah, that's basically trying to answer your question.
It is.
All right. So for your assignment, so section 11.2.4.e, don't worry about it. develop plasticity or to model or to program a finite element analysis software to model plasticity, you might want to look at it. But otherwise, you don't have to worry about it. For your assignments, you're given an engineering stress strain curve, and you need to first make it into a true strain curve. Then find the point at which the material starts to behave plastically and draw the relationship between true stress and the plastic strain parameter, and find the yield stress given the two criteria, 0.2% offset and the 0.5% strain. So this is A, B, C. D, find the Ramberg-Osgood approximation to this. And to find the Ramberg-Osgood approximation, you're going to have a few points and find N and K to best fit these data points. And as I said, it's easier to model if you try to fit this. You might get into trouble. If you try to fit this, you might have some trouble, but if you fit this, it will be easier. Now for E,
there is a function in mathematical which fits the data. What's the name of function?
I give you 3 different functions. You can try fit, find fit, or you can program it yourself using minimization by the sum, just minimizing the square of the error. In the third, number E, you're given 3 different stress states. And we want to know, and these stress states, the stresses, you've got sigma 1 is equal to negative 134. I'll give you an example. Sigma 2 is equal to 241, and sigma 2 is equal to 53 MPa. And so you're given 3 stress states, state 1, state 2, and state 3. For these 3 stress states, we need to find the elastic strains, the plastic strain parameter. So we need to find the elastic strains and the plastic strain parameter. Now the elastic strains are simply the relationship between the stress and the strain. The relationship does not change any. The question is, what is the plastic strain parameter? So you have to follow a few things. The first thing is yield function. Is sigma. What is sigma von Mises minus sigma yield? If it's less than 0, then there's no plasticity. If sigma von Mises is greater than sigma yield, then I can't do anything. I have to find the point at which sigma von Mises reaches sigma yield. And to find the point at which sigma von Mises reaches sigma yield, I have to know how these stresses increase. Because if all the stresses increase together, it's different from if I load in sigma 1 and then later load in sigma 2. The material, the plasticity is history dependent. So I really need to know how I reach this state of stress. Now it's given here that these stresses increase linearly together. So you can assume that your stress matrix looks like this. Negative 134T, 241T, 0, 53T, 53T, or T is less than 1. And find T at which sigma 1 means equal to sigma 8. 90%, 50%, whatever. So 50% of that stress state, that's when we started reaching yield. So we reach yield at this, so this is your sigma 1 means minus sigma yield equals 0, find T. Then I need to then find the consistency, find the change in the plastic strain parameter. So I need to use the consistency condition. Which states that an increase in the elastic strain parameter has to do with this. Because as the stress increases, so we found that the stress reaches yield at 50%. The stress matrix, when at 50%, when T is equal to 0.5, I've reached yield. So now the stresses are going to increase. As the stresses increase, the amount of plastic strain in the material will increase. I want to know how much plastic strain will increase. To know how much plastic strain increase, I have to incrementally increase the stresses. So I have to assume some increments in the stress. So I know from 50% to 100%, I'm going to divide this into however many increments you want. 2 MPa, 5 MPa, 10 MPa, whatever. So you divide this into increments, and throughout the first increment, there is a plastic strain developed inside the material. This plastic strain developed inside the material is obtained from this equation. Knowing the slope, and knowing this, and knowing the increments, I can find the increase in the plastic strain parameter. And for the three states that you're given, one of them will be elastic, one of them will be plastic, but very close to the yield, and the third one will be plastic, but far from yield. And for question F, describe 3 different history paths that lead to the stress state So, in linear elasticity, or in elasticity in general, 430 MPa is always associated with the same strain. If this is an elastic material, 430 is always associated with the same strain. But for plasticity, things are history dependent. You can reach 430 in many ways. You can just load until this point. Or you can load beyond this point to whatever you want and unload. And so you get 430, but with a totally different amount of strain inside the material. It's the same elastic strain, but different zero state, different plastic strain. Or you can load here, unload, and reload. So there are many different ways for which you can reach to this stress state. So that will be your assignment. Now I suggest that everything that we did today, that you do it again by hand. And look, this assignment will be, it shouldn't take time. So I would suggest that you also look at the next assignments. And in your notes, all the different. So I've asked you to solve a few problems for your assignments, but some problems I did not ask you to solve. However, these other problems were the ones that appeared in the previous final exams. So they are here. Also take a look at them and see if you're able to solve them or not. All right, and we'll see you next week.